Today we're going to explore one of the most fascinating phenomena in microfluidics, passive valves that behave like logic gates, even though they're just shaped channels with no moving parts or electronics. Here's the paradox that seems almost impossible at first. How can a simple piece of plastic with channels carved into it control the flow of liquid in a programmed sequence, start and stop fluids, and create complex timing patterns, all without pumps, valves, or power? The answer lies in one of the most fundamental forces in nature, surface tension and the capillary pressure it creates. Let me first describe what we're talking about. A capillary microfluidic chip is typically a small device, maybe a few centimeters across, made of plastic or glass. It contains tiny channels, often tens to hundreds of micrometers wide, etched into the surface. You place a drop of liquid at the inlet, and remarkably, the liquid flows through the channels on its own. There are no pumps, no external power sources, nothing pushing the liquid. It moves purely by capillary action, the same phenomenon that allows plants to draw water up their stems. To understand how this works, we need to start with the fundamental equation that governs capillary pressure, the Young Laplace equation. Delta P equals gamma times the sum of 1 over R, 1 plus 1 over R2. Here, delta P is the pressure difference across a curved interface, gamma is the surface tension, and R1 and R2 are the principal radii of curvature. For a liquid advancing in a cylindrical microchannel, we can simplify this. If the channel has a circular cross-section with radius r, one radius of curvature is r, and if we assume the meniscus is hemispherical, we can write a simpler form. Delta P equals 2 gamma cosine theta divided by r. This is the capillary pressure. Theta is the contact angle between the liquid and the channel wall. The contact angle is absolutely critical. It determines whether the surface pulls the liquid forward or pushes it backward. If theta is less than 90 degrees, the surface is hydrophilic, and cosine theta is positive. The capillary pressure is positive, pulling the liquid forward. If theta is greater than 90 degrees, the surface is hydrophobic, and cosine theta is negative, creating a barrier. Let me give you some concrete numbers to make this tangible. Consider water with surface tension gamma equals 72 millinewtons per meter at room temperature. The contact angle on clean glass is about 20 degrees. Let's calculate the capillary pressure in a channel with radius 50 micrometers. Gamma equals 0.072 newtons per meter. Theta is 20 degrees, and cosine of 20 degrees is approximately 0.94. The radius r is 50 micrometers, which equals 50 times 10 to the minus 6 meters. Plugging into our formula, delta P equals 2 times 0.07, 2 times 0.94 divided by 50 times 10 to the minus 6. This gives us approximately 2,710 pascals, or about 2.7 kilopascals. That's roughly 0.027 atmospheres, which may seem small, but is significant at the microscale. Now here's where it gets really interesting. By changing the geometry of the channel, we can create pressure barriers that liquid cannot cross until certain conditions are met. The first mechanism is a sudden expansion. When a narrow channel suddenly opens into a wide chamber, the capillary pressure drops dramatically. The liquid flows easily through the narrow channel due to high capillary pressure. But when it reaches the expansion, the effective radius increases dramatically, and the capillary pressure drops below what's needed to overcome the surface tension at the new, wider interface. The liquid stops right at the expansion. It forms a meniscus there and won't advance further on its own. But here's the clever part. If you continue to add more liquid at the inlet, you increase the hydrostatic pressure. Once that pressure builds up enough, it can overcome the barrier. The hydrostatic pressure equals RHO-GH, where RHO is liquid density, G is gravitational acceleration, and H is the height of the liquid column. For water with density 1,000 kilograms per cubic meter and our barrier of 2.7 kilopascals, we need a height H equal to delta P divided by RHOG, which is about 0.27 meters or 27 centimeters. But wait, in practice the barriers are smaller, and heights of just a few millimeters can trigger the valve. The second mechanism is even more elegant, patterning surfaces with different wettabilities. You can create hydrophobic patches that act as barriers. Imagine a channel where most of the surface is hydrophilic, treated to have a low contact angle. But you create small patches that are hydrophobic with a high contact angle. The liquid flows easily through the hydrophilic regions. But when it encounters the hydrophobic patch, cosine theta becomes negative, and the capillary pressure reverses. The liquid stops. At the barrier, delta P barrier equals 2 gamma cosine theta hydrophobic divided by R. If theta is 120 degrees, cosine is negative 0.5, and the barrier pressure is negative, actively repelling the liquid. Now here's where it becomes truly remarkable. By arranging multiple valves in sequence with different activation pressures, you can create a timed sequence of fluid delivery. You might ask, how do you program a sequence with no computer, no electronics, just geometry? The answer is beautifully simple. Each valve has a different threshold pressure based on its geometry. Valve 1 might need 1 kilopascal to open. Valve 2 needs 2 kilopascals, and valve 3 needs 3 kilopascals. As liquid accumulates at the inlet, the pressure builds. First, valve 1 opens when pressure reaches 1 kilopascal. Liquid flows into chamber 1. Then valve 2 opens at 2 kilopascals, filling chamber 2. Finally, valve 3 opens, and so on. This is logic encoded purely in geometry. The chip executes a program written in the language of surface tension and channel dimensions. These devices aren't just laboratory curiosities. They have real applications, especially in point-of-care medical diagnostics. For example, in an immunoassay to detect a disease marker, you need to deliver different reagents in a specific order. First the sample, then a wash buffer, then a detection antibody, then another wash, then a color-developing reagent. Traditionally, this requires complex equipment, with multiple pumps, valves, and precise timing control. With passive microfluidic valves, you simply add the sample to the inlet, and the geometry does the rest. The reagents are preloaded in different chambers, and they're released in sequence automatically as pressure builds. Now let's discuss something more subtle: metastable states. These valves don't have sharp on-off thresholds. They exhibit hysteresis. Hysteresis means the pressure required to open a valve is different from the pressure at which it closes. This creates metastable states where the liquid is temporarily trapped. If you plot flow versus pressure, you see a hysteresis loop. The valve opens at a higher pressure, but closes at a lower pressure. This creates a memory effect in the geometry its eyes. To predict how fast liquid advances in a channel, we use the Washburn equation, which describes capillary-driven flow. L squared equals gamma r cosine theta divided by 2 eta times t. Here, L is the distance the liquid has traveled, eta is the dynamic viscosity, and t is time. Notice that L is proportional to the square root of time. This is characteristic of diffusive-like processes. Capillary flow slows down as the liquid advances because viscous drag increases. Let's calculate how long it takes to fill a channel. For water with ETA equals 0.001 Pascal seconds, gamma equals 0.072 newtons per meter, theta equals 20 degrees, and R equals 50 micrometers, filling a channel 1 centimeter long. L equals 0.01 meters. Rearranging, T equals 2 eta L squared divided by gamma R cosine theta. Plugging in the numbers, T equals 2 times 0.001 times 0.01 squared divided by 0.07, 2 times 50 times 10 to the minus 6 times 0.94. This gives approximately 0.59 seconds, so a 1 centimeter channel fills in less than a second, which is quite fast. Let me walk you through designing a 3-stage device with timed reagent delivery. Stage 1. The sample enters through a narrow channel with radius 30 micrometers. This creates high capillary pressure, about 4.5 kilopascals, so the sample flows in quickly. Stage 2. The channel expands to radius 100 micrometers. Capillary pressure drops to about 1.4 kilopascals. The sample stops here until enough liquid accumulates to build pressure. Stage 3. The channel expands again to radius 200 micrometers. Capillary pressure is now only 0.7 kilopascals. This valve opens last, releasing the detection reagent. The entire device operates completely passively. Add your sample, and chemistry happens in the correct order automatically. Here's an interesting question. Can you make liquid flow backwards in these devices? The answer is yes, using hydrophobic barriers. If you create a hydrophobic region after liquid has passed, it can create a negative pressure that pulls liquid back. Researchers have even created switchable surfaces whose wettability changes with pH or light, enabling even more complex logic operations. Let me give you a powerful analogy. These passive valve systems are like mechanical computers from the 1800s. Just as Babbage's analytical engine could perform complex calculations using only gears and levers, these microfluidic chips perform complex fluid handling using only geometry and surface tension. The program is literally built into the hardware. The geometry is the code. Of course, these systems have limitations. Let's be honest about the challenges. First, evaporation can disrupt the timing if channels are open to air. Water evaporates, changing volumes and pressures. Solutions include sealing the device or operating in humidified environments. Second, air bubbles are catastrophic. A single bubble can block a channel completely because surface tension prevents liquid from flowing around it. Solutions include careful filling protocols to avoid introducing bubbles and designing bubble traps that capture them. Third, manufacturing precision is critical. A channel that's supposed to be 50 micrometers but is actually 55 micrometers will have a 10% difference in capillary pressure, which can break the logic sequence. For those interested in the cutting edge, researchers are developing capillary pressure networks, where multiple channels interact through shared chambers. These can implement Boolean logic gates. An AND gate requires liquid from two input channels to fill a chamber before it overflows to the output. An OR gate allows liquid from either input to reach the output. Here's a schematic of a microfluidic gate. Two input channels A and B feed into a small chamber. The output channel is at the top with a narrow opening that requires the chamber to be full before liquid reaches it. Both A and B must deliver liquid for the output to activate. The implications of this technology are profound, especially for global health. These devices enable low-cost diagnostics that work without electricity, without trained operators, without refrigeration for reagents. Imagine malaria testing in a remote village. A health worker pricks a finger, adds a drop of blood to the chip, and 10 minutes later gets a color change, indicating positive or negative. No lab required. The cost target for these devices is under $1 per test, making them accessible to the world's poorest populations. Let's step back and think about the bigger picture. These devices teach us something profound about the nature of complexity. Complex behavior can emerge from simple physical laws. You don't need active control or computation to create sophisticated function. Nature uses this principle everywhere, from protein folding to pattern formation in embryos. Geometry and chemistry encode information without any central processor. Let me summarize the key concepts we've covered. First, capillary pressure is inversely proportional to channel radius. Smaller channels create higher pressure. Second, contact angle determines whether a surface attracts or repels liquid. Hydrophilic surfaces with theta less than 90 degrees pull liquid forward. Third, sudden expansions create pressure barriers that function as passive valves. Fourth, multiple valves with different activation pressures create sequential logic programmed into the geometry. Fifth, applications include point-of-care diagnostics and lab-on-a-chip systems for resource-limited settings. I want to leave you with a final thought about the beauty of passive systems. Sometimes the most elegant engineering solutions come from subtraction, not addition. By removing pumps, sensors, and electronics, we create simpler, more robust, more accessible technology. Surface tension is not just a physical force. It's a computational medium, capable of encoding and executing programs written in the language of geometry. The paradox we started with is resolved. Logic can emerge from physics alone when we design systems that exploit the intrinsic properties of matter at small scales. No electronics required, just clever geometry and the fundamental laws of nature.